Hi, I'm going to show in this video how to fit an EPR spectrum from a copper 2 complex using EasySpin, but instead of using Matlab, which is closed source and not free, we're going to use EasySpin running in Octave using a version of the program that I modified to run in Octave from the released open source code of EasySpin. I first want to acknowledge and thank Professor Stefan Stoll and his group for making EasySpin available as open source, allowing many of us to modify the code and adapt it to other platforms. This code has a limited functionality compared to EasySpin running in Matlab, and that is because there are some incompatibilities between Octave and Matlab, and there are many things which have to be fixed in the code in order to eliminate some errors. Please don't expect full functionality. Also, it will be slower than running in Matlab, but for many purposes it will work. Here is my repository. I will put the link in the description of the video, and you can go to code, download zip, and you can download the whole folder into your computer and you unzip it, and then you have to do a couple of things inside Octave, which I'm going to show now. Here we are inside Octave. This is version 9.1, and the first thing you need to do is add the folder with the EasySpin files into the path from Octave. So you go to Edit, Set Path, and in here you go to Add Directory with subdirectories, and you have to go and find the version that you downloaded from GitHub. So in here, I already have this on my path, so I don't need to select it again. You can see here that I have the folder from EasySpin with all the subfolders. So you press save and close, and then the folder would be in the path from Octave. So you can run executables there. In order to start using EasySpin, you need to compile it. For that, you type EasySpin compile, and there are a few files which will be compiled. That means they are written in C++ inside Matlab or Octave, and they will be compiled to executables. And this has to be done because these functions are very performance critical, so they need to be fast. So in here you will see that there are some errors. This is because some of the things that Octave is trying to compile are incompatible between Octave and Matlab. These errors can be fixed, but I haven't had time yet to do that. So if you want to use the EasySpin chili function, you're going to have some errors. Out of 8 executables, 2 have failed, 1 of 8 and 3 of 8, but the others have been correctly compiled. So a lot of the functionality will be available, but not everything. Here is the file that I'm going to use for simulating and fitting a copper 2 spectrum arising from a reduced copper core. It is an anisotropic spectrum, and it's fairly complicated, but can be simulated and fitted appropriately by following these instructions. I can provide this file as an example. So what I'm doing here is basically reading an EPR spectrum file, which is saved as an ASCII in my computer. And this is for reading like 2 columns of numbers. I have to do this because some of the functions for reading files from Octave, like import data and others, are giving some problems, but there are many workarounds to do this. So this is one of them. And then what I'm doing is basically reading the information from that output structure spec data into the magnetic field B and the spectrum. And then I'm doing some normalization and subtraction of the mean, but this is not always necessary. This crop is that I'm removing some points at each end of the spectrum because basically there's no information there, and it allows me to see the spectra in more detail while I'm fitting, but I'm not really losing any information by doing this cropping. You can adjust this number manually for your spectrum. So then what I'm defining is the spin system. This is EasySpin. I'm not going to go over the meaning of all the parameters. What I'm saying is that I am defining a G-tensor. This is an anisotropic G matrix. These are the diagonal values. A line width. This is Lorentzian line width. I'm defining a copper nucleus and 14N nuclei because this is a corol, which is a porphyrinoid, has copper N4 coordination site. And I'm defining the hyperfine interaction for the copper ion and the hyperfine interactions for the nitrogen. There are two types of nitrogens, but they are very similar. And then I'm putting all these hyperfine matrices inside another structure, which is actually inside another matrix, which is the A matrix from the spin system. In EasySpin, you need to define a spin system. The A frame means that I'm basically, the four nitrogens are pointing in different directions. There's some symmetry to the molecules. So what I'm doing is giving the rotation angles for each of the hyperfine matrices for the nitrogen atoms. They are basically on the edges of a square. Each number, like -3 for example, is multiplied by pi/2. That's a 90-degree rotation or a 270-degree rotation in a certain direction. This can be found in the EasySpin examples in the EasySpin webpage. And then I'm defining an isotropic strain, and then I'm defining the Varae fields. These are the amounts that each part of the spin system will be allowed to vary during the fitting procedure. Then I'm defining some simulation options. So op.method equal perturb2 means that I'm using perturbation theory for the nitrogen nuclei, and I have to do that because, actually, sorry, for all the nuclei, I have to do that because otherwise it would be impossible to diagonalize such a large matrix. So perturbation theory is very necessary in this kind of system with many nuclei. And then I'm defining the experimental frequency range, and number of points, temperature, etc. And I'm doing a simulation with the parameters. I'm using the Pepper function from EasySpin, which simulates solid state EPR or frozen solution. It would be the same. And I'm doing this to basically plot the simulation from the initial parameters. Then I'm defining some fit options, and I'm going to do a Monte Carlo run for 5 minutes, and I'm going to fit the simulated spectrum to the experimental one, and I'm going to plot that after 5 minutes, and then I'm going to read the optimized spin system parameters into a second simulation. I'm doing that because I want to see the progress of the fitting. The interactive fitting that EasySpin can do in Matlab doesn't work here in Octave. At least it doesn't work in my version, and I don't know how to fix that part. So I'm doing a semi-interactive fitting. And then after this would be the second set of optimized spin systems, I am doing a Simplex algorithm to refine the results from the Monte Carlo runs. The Monte Carlo runs are basically random, or there's some random component. So it's an exhaustive search, but it will take very long time to find good parameters. So it will help you approximate the parameters, especially if you give it a small variation range for the parameters, which is based on the observation of the spectrum. You know, you have to eyeball the parameters as good as you can before the fitting. And then the simplex will go to a local minimum in the fitting procedure. So I'm going to plot these things. This will take a while. I will go here to save file and run. It should work. It will take some time. You can see here the simulation using the starting parameters. These already look quite good because I have already been fitting this spectra before, so I already put numbers which are very close to the correct ones. You can see here that now it's doing a Monte Carlo simulation. Sorry for the font size, I cannot change it right now. And it's giving me the best simulation so far, but it is only printing numbers. It will only show the spectrum after it has finished. So that's why I'm doing like 3 separate runs, like 2 Monte Carlo and 1 simplex. So I will see the intermediate improvement in the fitting. That's why I said it is semi-interactive. In Matlab, it will also take some time, the fitting. The only difference is that if you use the graphical mode in EasySpin in Matlab, you will be seeing how the spectra are improving in almost real time. So in here you have to wait a little bit, but the script works, which is important if you cannot afford Matlab. In here, I'm giving 5 minutes to the first Monte Carlo, then 3 minutes to the second, and then 2 minutes to the simplex. So you can see here that the first Monte Carlo has finished, so the simulation has improved a little bit. So here we can see that the second Monte Carlo has finished. The improvement is very small from the first Monte Carlo to the second, but there's maybe some improvement. And now we will run the simplex, which takes only 2 minutes, and it should refine the parameters a bit. So here we can finally see the result of the simplex. So again, the improvement is very small. I already gave it parameters which were very close to the correct ones initially, and then the amount of time that I allowed it to fit was small, so there's not a lot of change, but this was not the point of this video. What I wanted to show is how to use EasySpin in Octave to simulate a complicated spectrum and fit it. If we look here at the end result, we can see that the simulation is quite good. There are some differences, but that is to be expected in a complicated spectrum because there are many small approximations that have been done. But what you can see here is first the hyperfine splitting from the copper in the parallel direction. In here you can see this position more or less amounts to the parallel G value of the copper. This amounts to the perpendicular G value of the copper. And you can see here all the super hyperfine splitting from the 4 nitrogen nuclei, plus a little bit of the hyperfine interaction for the copper in the perpendicular direction. So this gives a complicated pattern of lines. Once again, I want to thank the creators of EasySpin. All I did was basically disable some warnings and delete some parts in the EasySpin source files, and it kind of worked. It works quite well in Octave, which is surprising because Octave is not 100% compatible with Matlab. But there are still some issues that I will fix over time. If you find problems in different functions and you know some programming and know how to help, you can of course clone the EasySpin repository from GitHub and improve it. I would be grateful if anyone can improve the code and make all parts of EasySpin work correctly in Octave. I think it is important to provide open source or free options to researchers in places that cannot always afford a commercial program like Matlab. So if you have found this video interesting and useful, please hit like and subscribe, and thank you very much.